Good afternoon, good morning, or good evening, good night, depending on what time of the world it is in your location. Welcome. Welcome to the Exida web seminar on optimal failure rate data. We'll move to the beginning of the presentation and then we will get started. I would like to remind everyone that this presentation is being recorded and that all registrants will receive a printout of the slides and a link to a recording of this seminar. So you don't really need to keep detailed notes, but you're welcome to, of course. This afternoon's webinar will be on optimal field failure data collection. And one of the reasons we're talking about this subject is because it has become relatively important, especially with some of the language in the new version of 61511. As we all know, or as we all believe, field failure data is the ultimate source of information needed to do probabilistic analysis. But of course, that data has to have really good, high quality, and we're going to talk about that this afternoon. My name is Bill Goble. I am one of the partners and a co-founder of exida. Most of my career has been spent in functional safety. I've been studying field failure data for about 3 decades, even before exida was started, because I used to work for a manufacturer, Siemens Moore, and we had lots of manufacturer's warranty return data. So I've been looking at field failure data now for about 30 years, and I have a lot of experience, which I hope to share with you this afternoon. I work for exida. exida is a global corporation with many locations around the world. Our most recent have been a new legal entity in Japan and a new office in Abu Dhabi. exida is a company that does a lot of different things, but all of our work is focused on automation systems, functional safety, cybersecurity, and alarm management. In the end, we think all of these activities tie in very nicely with those particular emphasis points. And we're quite proud that the ARC Advisory Group study has shown that in the certification portion of our business, exida has done about 2/3 of all the certifications in the world. And I'm really proud of that particular accomplishment of our certification group. I believe that's probably due to our high technical quality and good service. exida also does a suite of engineering tools. We call this suite Excellentia, and one of the tools in the suite is the SIL-STAT tool, specifically designed for field failure event database creation and maintenance. One of the sources that exida uses to gather up a lot of field failure data. Why are we even talking about gathering up field event data, field failure data? The answer is that one of the fundamental concepts in IEC 61508/61511 is probabilistic performance-based system design. I remember it was hotly debated during the committee meetings of the late 1980s and 1990s. Many people were opposed to this entire concept. Many still are today, but it has been shown to be a valuable technique, especially if the data is high quality. That's what you get with field failure data. We need field failure data throughout the entire safety life cycle. In the analysis phase of the safety life cycle, where we ask the question, how much safety do I need? We need process event data to figure out and help us identify potential hazards. In other words, what can go wrong? We need failure data to tell us in layer of protection analysis, what is the likelihood that our layer of protection may work or not? Of course, we need process data to indicate consequences of particular hazards. And all of this is real important in order to do a good job of figuring out how much safety we need. In the realization phase, we need data. We're answering the question, how much safety does my design have? And of course, when an engineer does a safety instrumented function verification calculation, the quality of the result is directly proportional to the quality of the input, especially the failure rate data. We also need failure rate data even in pre-selecting components often, because it's one of the key variables involved in picking one particular device versus another. In the operation phase, where we're answering the question, how will I keep it safe? That's where we can gather really good, effective, high-quality failure rate data if we do it right. You might wonder, okay, I'm talking about gathering up field failure data, and I'm talking about strong language in the new version of 61511 describing the need to gather up field failure data. And yet I've heard a lot of people for a long time talk about all the reasons they can't gather field failure data. Okay, we don't have time. We don't have a budget. We don't have enough staff. We don't have a procedure. All right, we do have to work on the economic justification of these things, but don't know what to collect. We don't have an SAP interface. Well, those things can, actually, in my opinion, can be quickly solved. Of course, there is a cost involved in that, too. And so what it all boils down to at the end of the day is justifying this on a cost basis. Now, we do have a couple seminars on cost justification of safety systems, so I'm not going to get into that in great detail today, except identifying it as a real problem that probably isn't as strong as we think. The fact is there's clearly an incentive to save money by gathering up field failure event data, and quite frankly, its process uptime is probably one of the major economic variables. In any process that's running at capacity, downtime is very expensive. And there are many other economic variables also. The key to success in any data collection system is getting high quality results. Okay, why? Let's talk about the reasons for why do we collect field failure data. We need to look at each application. Over and over again, I have seen field failure reports that indicate what I call an incompatibility between a particular instrument and an application. And what that really boils down to is process-wedded instrumentation, sensors and valves, and often it's a matter of materials incompatibility with the chemistry of the process. I've seen pictures of valves that have been eaten away. I've seen pictures of diaphragms and pressure transmitters that are shattered. And one great thing about manufacturers' warranty data is that often the manufacturer will trace the cause of the problem back to root cause. And many of those root causes have been identified as material incompatibility. That's important. We need to look for that, and when we find it, we need to change the instruments, or at least change the material in the instruments very quickly to avoid future failures. Number two, data can be analyzed to see if plant failure rates match the data used during LOPA and PFD calculations. Why would you do that? I'm not going to do these calculations over again, you might be thinking. Well, what if the assumptions you made, the databases you were using, do not match the reality of your site? You really need to know that, or perhaps you're not getting the risk reduction you thought you would on the pessimistic side, and perhaps you're getting much better risk reduction, and you might be able to increase the proof test interval. So either way, you really need to know. I have seen field failure data, looking at number 3, used to justify new maintenance activities. In fact, you're talking about cost justification. I've seen the field failure data used to justify additional or higher quality maintenance activities. And of course, most importantly, we need to look for problems that reduce process uptime if we really want to get an economic justification. We need to look at both failure event data and process event data. Now, there are some who don't believe realistic failure data is possible. And I do chuckle when I see this Dilbert cartoon created by Scott Adams. This really was published in a paper I was reading one morning. I laughed a lot. What I'm really worried about is the people who don't laugh. It's hard to imagine someone would think this is real, but I worry about that. Field failure data is not new. Field failure data collection has been done for decades, many decades. In fact, since the beginning of reliability engineering. I remember in some of the early textbooks I was able to find on reliability engineering that field failure data collection was done during the 50s and 1960s. And that's how the entire science of reliability was developed, by looking at this information and creating mathematical models for future prediction. Industry databases are one source where many different companies pool together and follow some common data collection procedure. I'll talk about that in a moment. Manufacturers' field return data studies have been done for decades, and manufacturers look for certain things, and that information is also quite valuable. And the primary reason is because manufacturers often will trace a set of failures down to the root cause. And by studying those, you get the failure down to the component level. There's a little bit of a problem there, is that manufacturers do have to assume what percentage of actual failures are returned, because they just do not know for sure. And of course, some manufacturers have a very narrow definition of what is a failure. I know when I worked in the field return section of a manufacturing company, I was taught to, well, let's just say I marked a lot of them not a problem, because that's what we were taught to do back then. End user field failure data studies are also perhaps one of the most valuable sources of information, but of course the data must be high quality, and I'll talk about what that means. Today, we are blessed to have industry databases from an organization called ORIDA, the Offshore Reliability Database Association, and it's a consortium of offshore companies in the North Sea. The program is operated by DNV in Norway, and the data analysis is done by top quality engineers from Sintef in Norway. And if you got as excited about the 2015 version of ORIDA as I did, you realize the tremendous amount of valuable information that's in that document. Now, I will admit it's a bit hard to use, and sometimes the population is low, like there's only 1 or 2 units, and that means there's a lot of statistical uncertainty when you apply a 70% or a 90% statistical confidence interval. But you can look back at the ORETA report from 2009 and earlier and get a whole lot of trend information as well as very good data. Now, I would like to mention that there is an ORETA analysis white paper that was done by exida, and we explain exactly what we were doing and how we did it. Let me get out the pointer. There we go. Please do not hesitate to read this paper if you get really excited about field failure data analysis, because at exida we do our work, we perform research, and we publish all that research in refereed journaled papers and present many of these details of the reference of the research in white papers. End user field failure studies. They represent an opportunity to even get site-specific failure rate information, which can be very valuable, especially for dealing with site-specific maintenance issues. However, this does have to be pretty high quality, and there are a number of problems that must be overcome. In many of the sets of reports that exida has been hired to analyze, we've discovered there's a lot of missing information that would have been valuable, that would have made the information set more valuable. We found different data analysis methods being used, some of which were optimistic and some of which were somewhat pessimistic. But perhaps the biggest issue of all is the definition of a failure. It's inconsistently applied. Let me give you an example. I will tell you that last year exida did an online survey of 16 specific examples of real failures. And we asked the survey participants to state whether they felt this particular example was, quote, systematic or, quote, random, based on the definitions from IEC 61508 and 61511. I want you to know that in all 16 examples, there was no agreement from the survey participants. When I looked at those results, I'm thinking, oh my goodness. No one in the world seems to have the same definition of what these two terms mean. So, it kind of means to me that these words don't have any meaning. And in this particular example, where we had a real failure that caused a real shutdown, 39% of the people surveyed called it systematic. Now, why is that important? In many data analysis systems, systematic failures are thrown away. Yeah, you heard me. They take the failure reports and throw them away. They don't count them. Even if they're real. And I will tell you that when the survey results were sorted by region, it was very clear that some areas of the world seem to think that most failures are systematic, and the failure reports are just thrown away, and you can imagine exactly what happens. The resulting failure rate calculation is extremely low, which can result in dangerously optimistic numbers to be used for probabilistic analysis. So you need to be extremely careful about throwing away systematic failures. The bottom line is any system or any data collection system that's of a high quality records all events without attempting to classify them random versus systematic. There are data collection standards. There's an ISO 14224, and I'm told a new version is just about ready to be released. There's IEC 60300-3-2, and of course in Germany they have an NE93 standard. And I'll have to say that in looking at all of these, the ISO 14224 standard stands out as being probably the best of all the standards I've ever read for data collection methods. So if you're going to have to buy one, I recommend the ISO 14224 as something you should look at first. What is a good field failure data collection system? Well, you must identify the components. You must record operating conditions, let's say, the application and the physical environment, because variations in both of those will have an impact on the failure rate. You have to record the volume of operating experience. In other words, how many unit operating hours do you have? For dangerous failures, the primary detection mechanism is a proof test, a manual test run periodically. Well, no proof test is perfect. So we need to know the proof test method, and therefore can estimate the proof test coverage, so we can actually estimate the real dangerous failure rate as opposed to the detected dangerous failure rate, because you're not going to detect all the dangerous failures. But with a little bit of knowledge about the proof test method and the coverage factor, we can actually estimate the real number of dangerous failures. And of course, it's a great idea to record the actual bypass time, because that is a significant variable in some circumstances, especially if the safety function cannot respond during a bypass. Think about it for a minute. Think about it for a minute. If you're proof testing, the safety function is shut down and you have a hazardous event at that moment in time, although it's highly unlikely, the safety function will not respond unless, of course, you have some special mechanisms or do some special proof test technique. A field data collection system really should be easy to use with minimal or no added work for the maintenance people. Because when you load maintenance people down with more work and they're already overloaded, field data collection just isn't going to happen. Bottom line is, it should take whatever you come up with, whatever method you come up with should take fewer man-hours than the current methods. Of course, you can't get fewer than 0, of course, if you have no current method, but hopefully you'll be able to justify everything, of course. Let's talk about these items. Identify the components. Ideally, we'd like the manufacturer and model number, and, if possible, even the serial number. With that kind of information, we can really track data and operating hours and reliability of a particular device very precisely. Of course, the data is still quite valuable without a serial number. And in some systems, the manufacturer model number, which of course tells us what kind of device it is, like a temperature transmitter or a pressure transmitter. If you don't have that information, at least identify the device type. For example, pressure transmitter. For every piece of equipment, we really should ideally understand the application, which is what we're talking about when we say operating profile, and the physical environment. depending on the device, physical environment may very well have a significant impact on failure rate. One way to identify that is to identify where the component is installed and record the physical conditions of the installation, which do not change once an installation is in operation, and a tag number and a hierarchy that starts with a unit, that starts with company and a site and plant and unit number. If we identify a location and the physical characteristics of the application are identified for that location, then it's really, you don't have to write every item separately. You can just identify it once. When we talk about volume of operating experience, we talk about when do you start a piece of equipment, when do you decommission a piece of equipment, and what's the operational duty? Is it continuous, 24 hours a day, 7 days a week, or intermittent, like it might be on a batch process? Oh, great. Let me stop. We got a question. Do all certified equipment come with a safety manual? Thanks for asking. All certified equipment should come with a safety manual, and I believe today all certification bodies are enforcing that rule. Some of the certification bodies did not enforce that rule prior to the 2010 version of 61508. I'm proud to say that at exida, we demanded that the manufacturers who got certified by exida have a safety manual even before the standard had very specific requirements for it. Now, I will say that a safety manual may be more than one document, and safety manuals may reference other documents to give you the complete story, but today, all certified equipment should come with a safety manual, and I'm pretty convinced that most everyone does. Thanks for asking the question. By the way, any question, anytime, please feel free to type it in, and as soon as I spot it on the screen, I can answer you verbally. What type of events should be recorded? Well, it's more than just a shutdown. It's more than just when a problem becomes well known. It's a proof test. It's, of course, any maintenance activity, including calibration. It's any diagnostic events when an automatic piece of diagnostics tells you there's a problem. It's a process demand and an actual trip. And it's also important to record process upsets or any false trips. Because remember, one of the key objectives of any data collection system is to identify the causes of false trips and to take action to avoid having them again. Because in many companies, they can be very expensive. For each type of event, we need to record it. What kind of type is it? Who did the work? And we record who did the work, not so we can blame them if the problem occurs again, but so we can go back and get more information as we need it. Please never use a data collection system to place blame on people. All that does is ruin the entire system. The date and the time a piece of equipment was removed from service and the date and time it was restored to service. Among other things, we're looking at the, we'll be able to calculate the, quote, mean time to restore. It used to be called mean time to repair, but really there's more than just repair. And other data depending on the exact event type. For proof tests, it's especially important that we record what device failed. In other words, if it was a final element assembly that had a solenoid valve, a quick exhaust valve, an actuator, and a valve, well, which piece failed? Was it the solenoid valve or the quick exhaust valve or one of the other parts? It's very important that we record as found conditions. Exactly what was happening when we first went out to find out what's going on. In other words, and if possible, write down the failure mode, write down possible causes as an opinion, the failure date and time, person who did the replacement work, if there is a work order system, the work order number, and perhaps most importantly of all, the date and time the safety function was restored to service. Because the last thing we want is someone to put a safety system on bypass and then forget to restore it again. One way to, of course, remember what we're trying to do is reduce the man hours, make it economically possible, and make the field failure data collection system optimal. One way to reduce the work is to create a tag database that has a lot of information about each device. The reason we do that is we don't want all this information being recorded manually every time there's a problem with a particular device. We want all that to come in with one entry, typically the tag number. Most of this data is needed for SIL verification calculations, and so a tag database for all safety functions can be established with a database transfer from the Excelentia tool. There are many other opportunities for downloading tag databases from all the various engineering tools used in a system. Data collection is important. It should be easy to do. And remember to record all events, proof test results, maintenance, repair actions, and process demands. Most needed information should be pre-programmed in databases because it's very important that we avoid unnecessary data entry. The information should be gathered automatically whenever possible. That's typically done by getting a set of event data, which is typically manually entered, and we're combining it with an instrument data record to create a complete event failure data record, which is a combination of both information. This is a diagram of how it's done in the SILstat software from Exida. Many other programs follow a similar technique. Here is a diagram from the ISPM software showing how the event failure records combine with what they call the equipment taxonomy and generate a failure record database, which then can be extracted to export into a data repository like ORITA or PIRD. PIRD is the AICHE, American Institute of Chemical Engineers, Center for Chemical Process Safety. That group established the Process Equipment Reliability Database, PIRD, which is a very excellent consortium to join. And both the ISPM tool and SILstat are capable of exporting data to PIRD in the PIRD format. Reliability Dynamics is a company that Exida works with, and it's especially appropriate when companies have SAP data work management software programs operating in their plant. Data collection is one thing, but data analysis is another. It's very important to have data analyzed correctly. And of course, at Exida, we use a group of very experienced reliability engineers because these people need to recognize data quality and flag processes that seem lower quality. Exida used a set of techniques which we have combined into a method we call predictive analytics, and of course there is a white paper reference at the bottom of the slide if you'd like to read about all the details of the predictive analytics method. For now, I will simply tell you that Exida has done a lot of work with a lot of different manufacturers. And for every product category, we have developed a good understanding of the variations in design strength, complexity, materials, applications, and environments. The FMEDA technique predicts a failure rate as a function of application type and operational environment. Knowing all of this, we can take statistical analysis of FMEDA results and produce upper bound and lower bound total failure rates and dangerous failure rates for each product type. We do publish these upper bounds and perhaps most importantly the lower bound on a website called SIL-Safe Data. SIL-Safe Data is published on the Exida website and can absolutely be looked at anytime you want to see if if your piece of data is well within range. I see another question. It says, where is SIL data? Now it's called SILSAFEDATA.com. It's on the Exida website. You can also find it by looking on the Exida webpage, Resource tab, and then SIL-Safe Data tab. And I'll show you why some of this stuff really works. A study of 35 different pressure transmitters combined with field failure data showed that we should expect, based on current designs and even older designs, in fact we have the data on many obsolete pressure transmitters as well as all currently, virtually every single currently produced pressure transmitter. And we know that any field failure data collection system should generate data within the green bars, the expected range. And we will check the output of a field failure data collection system to see if it's generating a number within the expected range. Now, it's also possible that the number could be within the outlier limits. And there are some, for example, some inexpensive pressure transmitters that just don't have much in the way of protection, and therefore they have a much higher failure rate. And that becomes very clear when you study the designs and the details of the design. And so we've established outlier limits, and we publish those on the SIL-Safe Data website. If you get a set of data within the outside of the outlier limits, we really have to look at that very carefully and make absolutely certain that the data collection process and the failure definition process are reasonable. For example, we looked at an extensive set of test results from a test shop on pressure relief valves. The shop was owned by a manufacturer and had an exceptionally low failure rate outside the outlier limits for the predictive analytic bounds. We were asked to visit the test shop when we said something seems wrong. And what we discovered, look at this for a minute. What we discovered was that every time a pressure relief valve was returned for testing, it was cleaned up before testing. Cleanup included disassembly and replacement of all the seals and O-rings. And I was thinking to myself, my goodness, they have refurbished the entire unit. I'm not even sure that any failures would occur after that refurbishment activity. Think about it. Oh my goodness. Lessons learned. The data collection and test process must be understood to correctly analyze field data. And most importantly, as found conditions must be recorded. In another example, we went to an on-site repair shop where a maintenance management system on a central computer was being used to manage work orders. And the system analyzed the failure rate by using a simple formula, number of failures divided by estimated operational hours. And the result came in as something that was extremely low. Yeah, I am sorry, all these examples came in extremely low, but a lot of people work hard to reduce the failure rates, even if that's unreal. Anyway, the system indicated the failure rate was very low, and therefore the proof test interval could be expanded. However, one of the instrument engineers visited the test shop and discovered that failure reports were only entered into the management system when a device was sent out for repair. And that's because you had to enter it in order to get a purchase order. If they could fix it in the shop, they didn't need a purchase order, and they did not take time to bother entering the data into the failure system. Wow! No wonder it was optimistic. The proof test interval was not extended, fortunately. And again, the lesson is we must understand the data collection process and the as-found conditions. Okay, got another question. Do the pressure sensor failure rates include failures due to issues about impulse lines being plugged? Good question. But the answer in this case, that particular analysis did not include manifold valve and impulse lines. It did include, well, in fact, we have the data with or without a remote seal. Impulse lines were considered separately. And of course, one of the reasons it's really important that you know that is when you compare data, you must understand if the impulse lines are included in the comparison or not. I think a good quality field failure data collection system would separate the impulse line failures from the transmitter failures, but there's still great value if they are not separated. The key is you must know whether the failure rates include impulse lines or not, because obviously in some processes, impulse line failures can be much higher than transmitter failures. But I will tell you the numbers on this particular slide did not include impulse lines or a manifold valve for that matter. What they did include in the average was remote seals and even high-low differential pressure remote seals, because we have exida has predictive data for remote seals. I mean, these kind of go on, and I don't want to overdo it, but the bottom line is the field failure study of a valve showed an extremely low failure rate compared to the PA. They were below the outlier limits. And of course, the manufacturer who did this study concluded that this particular control valve would be an excellent choice for safety applications. And although it was not stated in the analysis report, and no information was available even when we asked for it, it's possible that the data was gathered for control valves used in control applications where the valves were moving. If the valve, in fact, was static, there's a bunch of different failure modes that can occur when a valve is not moving that just do not occur when a valve is moving. So the failure rates for the same product in a static application would be much larger than that product in a dynamic application. Point: application conditions must be recorded. One of my favorites was the fact that in one study, before the data was analyzed, systematic failures, whatever that is, whatever that word means, were eliminated from failure counts. I mean, it says to do so in the standard. What it doesn't do in the standard is give us definitions of random versus systematic that everybody in the world understands the same. Our survey proved that. Now, if we eliminate a pile of failures, the analysis will give us a much lower failure rate. And in this case, the numbers were substantially below the outlier limits for the mechanical equipment. An interview at the site revealed that a number of contributors to the database were doing failure categorization. They clearly understood in their mind that most mechanical failures are systematic. And that attitude can be supported by logic. However, the results are very unrealistic unless procedures and designs are changed to eliminate future versions of every failure. The bottom line is, all real failures must be included in a data collection system, whether they're, quote, systematic or not, unless it can be proven that procedures and/or designs are changed to eliminate future instances of that failure. Oh, got another question here. Let's see, I can only see the... Okay, how do we manage to reduce the number of failure modes when the specific failure modes are not included? There is what's called a taxonomy in many of the data collection tools, which list a set of failure modes for each product type. At exida, in the FMEDAs, for example, for sensors, we published more than just safe and dangerous. We published fail high, fail low, fail diagnostics, and of course fail dangerous, which is primarily frozen output. So we don't pre-categorize everything the way some of our competitors do. Still, we don't identify the specific failure modes because our FMEDA reports are designed for safety instrument and function verification purposes. I would say that the tools, for example, the SILSTAT tool, however, has a series of real failure modes, which you will see in real operation. The ISPM tool has a list of real failure modes, which you can pick from, which are also quite realistic because they came from the PERD committee. And the ISO 14224 also has many of those failure modes listed as well. Now, you want to reduce the number of failure modes. Yeah, basically so do I, because it's hard to choose from a longer list as opposed to a shorter list. And so at exida, in the SILSTAT software, we have reduced the list. We have combined many of the similar failure modes into one particular description in order to simplify things. And I think at the moment, all ideas are welcomed, but I believe that's the best that we can do. You've seen from a number of these examples that it's absolutely possible to have some very unusual results. One of the things that I found fascinating was that several data sets have indicated there's a 3 or 4x difference in the failure rate from one site to another. Yeah, that's what I said. 3 to 4x difference in the failure rate from one site to another. In one particular study, it was one company And the processes were the same process in two different sites, and there was a 4x difference in the failure rate. Well, in that case, root cause analysis showed the difference is primarily to do with differences in how engineers picked the equipment, how they did their maintenance, how they did their testing, and how they did their repairs. And so we were able to use the field failure data to identify site-specific failures and really identify ways in which the particular site procedures could be vastly improved to reduce failures and primarily to reduce downtime. The bottom line is that a good data collection system, we believe, can be implemented without a major expense. A good data collection system with predictive analytics can provide consistent results across many different sites and applications, especially when we analyze site-specific differences. I hope you found some of this information useful. Please do not hesitate to type in any questions you might have right now, any comments, any challenges, anything that didn't sound right to you. And if a question pops into your mind later, please do not hesitate to send us an email. You can use the info@exida.com and we'll answer you in an asynchronous basis. Let me just scan and see if anybody has any other questions right now. I'm not seeing anything coming up. I'll give you a few more moments to type in any questions that you might have. In the meanwhile, I'll just repeat. If a question pops into your mind when you get a copy of these slides, or if you look at a recording of this session, please don't hesitate to send us an email, and we'll do our best to get you a relatively quick answer. But we operate asynchronously. That's the advantage of emails. Well, since there are no more questions, let me just say thank you very much for your participation. We appreciate all comments on the quality of the presentation, the quality of the material, and the relevance of the material. We'd very much like to make the exida web seminars valuable to you. So give us all your feedback, please. In the meantime, thank you very much for your participation. Please attend next week as well. Goodbye.